like that. Did anyone else hear
Microsoft
that?
Selena.
Yeah, I heard that.
Oh,
Okay,
yeah,
I just
yeah.
wanted to
It's
make
like an
sure.
off-brand Siri.
Yeah, that's epic. And then I got a screen share to the proper one of my 4 monitors.
You have 4 monitors?
You bet. And every other monitor besides the one you're seeing is full of me with like 1600 tabs open on the Arduino wiki at any given time.
Your computer must hate you.
No, my computer's epic. It's got 32 gigabytes of RAM and it's all used for Chrome. All right, so
Yeah, that's
Absolute
the
gold.
true point
I
of
love
having
it.
32 gigabytes of RAM.
that's my
Just to
that was
run
my
Chrome.
that was my strategy. All right, the first question you had, Samuel. Wait, am I not able to? Let me open the participants window so I can see who's talking. Oh, and there's also people still trying to join, so I have to watch that too. There we go. All right, everything should be situated. So you asked about question 4, so you wanted to talk about method for the start and end addressing here.
While I was doing it and I was going through the recording,
Yeah.
at least it seems to me is if you take this is going to sound really weird, but if you take 2 to the square root of n being the number of kilobytes,
Yes.
minus 2, that gives you the range.
It should. That's what that E is, since we're word addressable here, and he's asking for, you know, and we're operating in the byte domain. It's aligned 2 by 2, so it makes sense.
Okay, I just wanted to make sure.
So let's do the example, the first one. Given this is flash, so we're given 32 kilobytes of flash. So you said that you did what? 2 to the amount of kilobytes?
Yeah, or no, not the amount of kilobytes. Whatever, because he's got 2 to the 2 equals 4 kilobytes minus 10 kilobytes. Whatever 2 to whatever value equals 32 minus 2 to the 10 or plus 2 to the 10. Sorry.
Well,
So
that'd be for RAM, but yeah, because that's 4 kilobytes is where the address space of RAM comes in.
Yeah, but when I ended up in doing it by hand, it still worked for everything else. So that's why I was wondering if I was doing it wrong. Because
so you said your strategy is given. You said 4 kilobytes here, so you want whatever value yields 4 kilobytes, which should be 2 to the 10. That's 4096 if I remember correctly. No, it should be 2 to the 12th.
No, it's 2 to the. I thought it was 2 to the 8th. For
2 to the 12th yields. You can see I think he meant to say plus there because it is 2 to the 12th. So yeah, 2 to the 12th yields 4096, also known as 4 kilobytes for, you know, weird reasons. So you did 2 to the 12th minus
2.
Just minus 2. And then you
Just
took that and you took that number to represent your upper bound.
Or the specific range. And so if you add that to 0, it ends up being 1 FE.
Well, in this case, your start address is 0400 for RAM for 4 kilobytes.
Excuse me.
So you'd add it to that instead. But yeah, that will get you your range. So the whole point of his math here is basically saying, here's the quick and dirty trick. He makes it a little more complicated than absolutely necessary, but his, you know, in doing it this way, he also, you know, really demonstrates what's exactly happening and why it's that. Because most people would just be tempted. Are there people waiting in the room? Yep. Most people would be tempted to just, as he mentioned, do the counting error where they'd say the end address of flash is 0xFFFFF, which is no, that's not how it's done. So we'll do an arbitrary example for anything. I'll just say we have 10 kilobytes of flash. Why not? Actually, no, that's not a base 2. We'll just take as 32 kilobytes of flash. 32 kilobytes of flash should be to the 15th power. Will yield 32,000, whatever. Let's check that. Yes.
So that'd be 2 to the.
2 to the 15th power is 32 kilobytes.
What's 2 to what is 32?
It's not. I guess you could try and do it in the reduced unit, but 2 to the 15th is 32 kilobytes in actuality, because you're not actually dealing with the number 32.
Yeah.
You're dealing with number 32 kilobytes, which actually has a little bit of extra tag done. The real number is 32,768.
Okay.
So when you see like the kilobyte unit, he made a mention about this, that there's the fake commercial kilobyte, gigabyte, megabyte units, which are in base 10, you know, 1,000, the next one's 1,000 times larger, that kind of thing. In reality, since everything's operating under base 2, it's not quite that way.
All right.
So 2 to the 15th power is 32 kilobytes. That's the first thing. So we've been given some information for 32 kilobytes here. So the first 512 bytes are reserved starting there. And that's for IO peripheral. And he said the top half is reserved for the 32 kilobytes. So the first thing to note there is if it's the top half of however much space you have total, address space is 2 to the 16th. So you have 64 kilobytes of total address space. Oh, wait, let's do this one real quick up here so everyone gets this part, because I had some questions about this. Does anyone have any problem coming up with the size here in bytes of the address space? Like, is there any question as to why it's 2 to the 20th power as opposed to 16, 8, anything like that?
Isn't it just because of the number of registers you have?
Not registers here. In fact, the number of registers would be deceptive. 2 to the 16th is wrong here. It's the fact that each register has 20 bits.
Okay.
So in that instance,
the maximum your PC can choose from is 2 to the 20.
Yeah, because a register, in theory, a single register could hold one single address. So the max address you can address to is 21s long. And then, that's going to give you 2 to the 20th. So that's just that. But the same process comes here because you have 64 kilobytes total space, because he says the upper half of the memory is consumed via the 32 kilobytes of flash. And then he tells you all this other stuff. And then he mentions that there's some empty sections, but we don't need to consider that part. So it's the upper half. So in this case for flash, you actually end up calculating the upper bound first in reality here. So you do memory is set in words in the MSP, as we all know by now, but we're given this in kilobytes. So to address the final top section of memory, you have to actually use the aligned address, which is going to be FFFE here. And that's just an important thing to remember. And that goes across all things. You're always accessing a little Indian byte when you're going in, which means you're accessing the lower one. And that's just how it is. So across the board, you should never, ever, ever see an F as your last hex digit in a question like this, because that's not possible in Little Indian architecture if you're addressing.
It is possible if it's
big Indian.
No, it's possible if it asks you
for the specific address of an upper
byte address.
Yeah.
This specifically asks for word addresses.
Yeah, so you got to be careful.
There is no word above FFFE.
Yeah, so you got to be word addressable here. But as Sydney mentions, if it goes to byte addressable, then yes, you can in fact have your Fs. But
I know that because the homework did that and I screwed it up.
Would the saying it's byte addressable, would that affect any of the range numbers?
Slightly, very slightly, but yeah. So instead, if this were byte addressable, this end address would be FFFF.
Yeah.
And that's about it. I don't think the starting address minds, because think about range, where even if you have units who are segmented in 2, which is how words operate, you're taking the lowest to the highest, except in our system, our highest is actually 1 away from the top, but our lowest is still the lowest since we're Little Indian. So if you're a big Indian, it'd be reversed. The bottom would be down 2, or I should say the bottom would be up 1 instead. It'd be incremented by 2, as opposed to having the top. But we're in the Little Indian architecture. So if you were to be byte addressable, the only thing that switches about the addressing, in this case ranging, is your end addresses here, because that's the only thing that's affected in Little Indian, because we're looking at lowers for the word, which is good for us. So all you'd be doing is incrementing the end addresses by 2 or by 1, but in reality, numbers, funny numbers.
So that's that. Okay. Can I potentially share something?
I don't know if I can, if I have that. Let me see.
Usually you can only share one at a time.
If it's too much trouble, then that's fine.
It's always weird. All right. I think I made it so you can share it too. Are you able to or no?
Yeah. wanted to share this specifically. That's what I've been doing.
How am I able to see you? Does
Says
anyone know how
choose
to
options?
Does
Oh,
anyone
here,
know how
there
to
you go.
switch between his share and my share?
It's at the very top of the screen. You have to like swap between whose shared screen you're looking at.
I can't
Sorry.
do
View
that. So what
options.
I'll do is I'll stop my own share for a moment.
Sorry if I'm throwing a wrench in the works.
Can everyone else see his?
I can see his.
All right. I think I'm restored. Okay, perfect. All right. We can all see yours and it's recording as
Yeah.
well. Continue.
That what I have up there is what I've been doing to convert from kilobytes to bytes and then -2 for the range. That
I see.
7 FFE, I subtracted that from, I believe he had what, FFFE, and that got me 800.
Yeah.
That's
That's
another way
exactly what
to-
I just did.
So if it's say it's byte addressable instead of word addressable, would I just remove the -2?
Basically.
Yeah, your upper address will be FFFF,
As opposed to that.
and that will equal.
Although that's your total range, and then I take it by adding the 800 here is what got you up to FFFE, and then in byte addressable mode FFFF.
Yeah.
Yeah, that's
And then
exactly how it should
versus on the bottom, I'd do the same calculation, but simply add it to my starting address.
be. Yeah.
I figured this would, I don't know. I just found this a lot easier to do than kind of his method.
32 kilobytes is 2 to the power of 5, huh?
No, 32.
Just 32.
The number
for
32.
number.
Oh,
So he's
I'm like, what?
reducing.
I'm
He's
con-
reducing it.
Yeah, I'm
I
converting
don't
it into
even-
bytes.
The way
Sorry.
I remember it is just a kilobyte is 1024 bytes.
Yeah, see the trick
From
here,
there-
the trick here is you're adding somewhat of an intermediate step. You see the 2 to the 5th is equal to 2 to the 15th. 32 kilobytes is just 2 to the 15th.
Oh, that's weird.
So
Yeah,
that extra bit, it doesn't change anything because the math's identical, but 2 to the 15th power, you could have just, if
Yeah,
you type 2 to the 15th in your calculator, it's still 32,000, like 700,
yeah.
whatever.
yeah.
So you'll get the same answer either way, which is good. So in word addressable, you got to subtract those bytes off the top to get to the proper zone. And then in, in in byte addressable, you don't have to subtract. So the trick here is he didn't give us the lower address range. He didn't give us the start address. We had to figure it out ourselves. So you calculated the range. The information he gave you is that you have all the way to the top, which is 0xFFFE, as we know, because of the rules. So you have to just figure that one out on your own. You then calculate the range as he's done here. And then you do 7FFE. And then you subtract the 2 to yield 0x8000. And that's how you get your lower. And the other questions were given the lower, which is very helpful.
I just wanted to confirm if that wasn't just a random trick that I happened to.
No, it's not a
You're right.
it's not a unique quirk of mathematics.
Okay.
In this instance. All right. Any other specific questions on, I'll reshare. Any other specific questions on stuff from this midterm before we move on to the old midterms? This one. I'll quickly roll through it. Any questions on this first stuff with a size, unsigned, signed size, like register field size?
Register field size got me a first.
This is how many bits it takes to access any of the 16 registers, so it should be 4
Yeah,
4 bits, yeah. So I guess it is a little wacky in the wording. We know
'Cause it's
we
like,
might not have been
what is it
introduced
needed?
to what that means.
to encode
Yeah.
one general purpose register.
When you ever see the word encode or anything like that, unless you're in a cybersecurity class, it's almost always referring to the process of decoding, which is a decoder which allows you to select between multiple, endpoints,
Yeah, I'm
as
thinking
opposed to,
about it from like the
cyber realm. Everyone understands these quick questions, the decrement increment rules, and then just the 1616 stack and status. I don't remember if the ISA has this information, what the registers.
It doesn't.
It doesn't. All right.
Oh,
So
yeah.
let's quick, everyone say it with me here. R0 is the
PC. Is the
program counter. And if you
And it
ever
contain-
mess with it, you will die. R1.
Wait, you mess with it all the time, Ethan.
They don't know that.
R1
Shush.
is the stack pointer. We mess with it a lot. You still probably will die. And then the final one is R2, the status register. And there is one extra low one that's, of great acclaim, being R3, which is the constant generator. Now, we don't talk about it all that much, but whenever we get to those weird questions where we're doing instructions and source, destination, addressing modes, then how many words is an instruction? And then you're looking at like in immediate and you see immediate 0, and then you question, why doesn't that count as a word? Well, it's because the constant generator, as Milankovic says, just pulls numbers out of thin air. So you don't have to count it as data. It can just do that. So I doubt he'll actually hit us with stuff like that. Every question he hit us with on this practice one, it tricked a couple of us up because we got stuck thinking it's happening all over the place. But in reality, it only happens when you use it in immediate mode or potentially indexed. But
no, not indexed. It's
so literally just immediate.
It is literally just immediate.
Then there we go. Only consider the possibility of constant generator in immediate. The couple constants I remember that are important in the constant generator that are reserved are 0, 1, 2, 8. Is that it?
1, 2, 4, 8, I think.
1, 2, 4, 0, 1, 2, 4, 8 or something like that. It's just like anything like that, like base 2 numbers, stuff that you could use for shifting across address spaces and such. Even so, that's what that is. We looked at that. We just did a bunch of stuff on this. This stuff is like, there's a reason it's only worth 4 points. It's very quick. The stuff that's worth a lot of points, like these saucy questions, also aren't all that bad because we have the ISA. So at minimum, you'll know what the instruction's doing, unless it's decimal add. But, you'll have a good time. So no questions on this since we went over it. It's just a thing that nobody really knows what decimal add does. It just does. Then there's question 5, which also went over. Anybody have any misgivings about addressing modes, addresses, instruction size? Instruction size is a good one. As mentioned, he emphasized in his message today and just all the time, read the question closely. Units matter, as they always do.
Yep.
In this case, it's bytes. I would expect to see it in words on the exam just because, I don't know. We've done it in words more than we've done it in bytes, in my opinion.
So you have 3 byte instruction sizes. It's 1.5 words.
That's what I'm talking about. But yeah, instruction size, that kind of thing. This is code deconstruction. Does anybody want to talk about this stuff on this one before we move over to the other ones? Because these are pretty fun.
Wait,
Yeah.
that's
this isn't. Yeah, no, never mind. This is just writing one.
Yeah.
This is the writing one. The true falses, which the past exams also have these directives that we don't know about, so we'll probably skip the first question. This is just running in your head.
This is also kind of a weird one though.
What does the even thing do?
And it even aligns, but that's
Yeah,
not
but
within
that's just
the MSP 430.
yeah,
That's more directive stuff.
Yeah, that's why he didn't do all of it, because we don't have certain directive stuff known. But he did most of it here. But
So,
all
like,
he did in the MSP architecture, everything's assumed even. You don't have to do it manually.
So the DC 16, DC 32, we don't have to worry about.
Actually, you know what? These are older directives, I bet.
They
'Cause
are.
now
Some
you
don't
use dot
translate.
even.
A lot of the
probably
directives
wouldn't
don't
anticipate
translate.
those.
They're not
Yeah,
gonna.
those
The
are
real ones
old.
aren't gonna be there. Yeah, old directives won't be there.
To see DC8, what is that? 8 bytes?
This is some type of
Or 8
directive that
bits.
allocates, like probably tells it that
So that'd
this
be
is
like
this is
dot
the
car.
data type of like byte, and then here's your array,
Yeah.
and then this is telling you this is a data type of word,
certain time,
and
yeah.
this is your value or whatever. That's what I would assume.
Oh yeah, we need to go over the size of like integers, long integers.
Yeah, let's do that quick. MSP, we've done a lab on this that was just horrible, but it was what it was. So we have the smallest one of them, which is the character, right? Or is it of the same size?
It's the character.
The character's 2.
Oh, it's a 1.
Oh,
isn't
it's
it?
1. Yeah, sorry, it's 1. 2 pairs, 2 hexadecimal digits, 1 byte. Character is 1 byte. Then we have int and unsigned int
Sure, 2.
are both 2.
Long just multiplies.
Both 2.
It multiplies it by 2.
Long int
long
brings it up
multiplies
to
it by
4
4.
bytes.
Oh, hold up. I'm trying to write this down.
Yeah.
Don't worry, I'll say it all again. I'm writing it down too, so I can
Right,
list
can
it
you
all
write
off.
it on like Paint or something, Ethan? That would be good.
I can, but no one's allowed to make fun of it.
Too late.
All right, let's see.
Unless you're actually writing with a pen, I don't think anybody's going to judge you.
I'm writing with a mouse like a
It's
Chad.
actually pretty good.
It was better than my MS Paint.
B is bite. I'm not writing out the whole last word.
How do
Capital
you
B.
spell Worcestershire
Put capital
sauce?
B.
Can you spell it out?
Worcestershire. Worcestershire.
I'm assuming when y'all are stating multiplying by 2, multiplying by 4, we're assuming that the basis is 2, correct?
Yeah.
We're gonna
Son.
call this the uint.
The micro int.
Yeah, which is also 2.
Please, I do not need scientific notation for this. That's going to make everything worse.
Then we have the long, which I'll just call the long here, which brings it up to 4. And when you go long int, brings it up to 8.
Yep.
And then you have float. No, we're not talking about that.
Float? You
Float, and the
refuse to
other
do
stuff
float.
just bring it up even bigger. It just gets bigger and bigger.
Well,
and bigger.
all you have to say is float is I think it's 8 bytes as well.
Yeah, and then there's one that's longer. Or I actually think
And
8's
double
the
is-
largest. Unless double's 32 or
Wait, hang on.
16.
It's 32 bits.
It gets pretty obnoxious, but I think the only ones we'll really need to consider for this exam. Where'd my pen go?
4 bytes for float, and then it's 64 bits, which is 8 bytes for double.
Yeah. Let me
But
make
they
got
can
that.
they can store a lot more precise information.
Yeah.
I really hope he doesn't ask a question about that.
You
Yeah.
have just jinxed us, good sir.
Yeah.
Oof, unfortunate. So that's that. So that's all like the sizes of stuff, just because that didn't, I mean, it had something to do with the question because these directives are methods of declaring, like this is DC8, probably declaring a byte array. This is
So a
DC,
car.
this, yeah.
Wait, whoa. How,
DC8, another DC8, which is another, this is an array of characters or just a character.
wait a minute.
somehow.
If that's car, then how is it storing -8? Oh no, it can store -8.
Yeah, it's just, it's a byte.
Yeah,
It's
yeah,
just
never mind.
8.
I'm stupid.
8, and then this is a word, and you can see it because this is like B, B, and then you see W, and then you see LW, which is 32. It's also like a long word or something. Oh well, we don't need to know about that because that's like a fake one. Did he like just skip stuff? I think he did.
Yeah,
He did.
because that old code.
Makes no sense. Yeah, okay.
I will say stay secure on your octal conversions because
Octal!
Yeah.
Does everyone know how to do the conversions between all bases? If I told you, what are you
I,
gonna
I
say?
can go from
especially
anything to binary and binary to anything. I
So-
cannot skip binary though.
If I were to ask you to give me the number 10 in base 10 and I say I want it in base 13, what can you do?
So
Base
decimal
what?
to base
Divided
13.
by
Base 13, I can just
13.
make it up. I can just make it up. Well, here's the thing. So yeah, you divide by 13 over and over and over again to yield your symbols, and you have to know what the valid symbols are. Of course, hexadecimal is base 16. So in 13, you just cut off the last 3 symbols, which would be, what is it? FED. F, E, and D get cut off. So your max symbol in base 13 is C, from what I remember. But it's a fake thing. But it's just like, the point is, if given decimal, you just do the whole division thing. But you can also just do the magic. Well, this is the binary. If you have a binary number, you want to convert it to anything, you can just do the 1 or 0 as the preface of a times the base. So this would be 13 to the whatever, bit it is, whatever number it is. So if we had a binary number 10010, that's 5 bits, and we wanted to convert this thing to base 13 for whatever reason, we would do the MSB, which is position 5, would be 1 times 13 to the 5th power. Yeah, something like that. That's that whole polynomial formula, but we're not actually gonna have to do anything at base 13. But converting to octal is just, so Binary to hex is quick because we all know that you can directly look at any 4 binary bits and immediately know what it is in hexadecimal if you just memorize the symbol table. So that's easy mode. But the problem is octal also is not that hard because you just sample at 3 bits instead of 4 bits. So the max symbol in octal is the number 7. So when you have 3 binary bits who are all 1, that yields you a 7 in octal. But here's the trick. Because of octal's annoying nature of being in 3s when we're in a base 2 system, unlike hex and unlike binary, the results in octal almost always need to be padded in order to actually make sense. Because, no systems we use run on 5 bits most of the time. They might run on 6, 8, 10, something like that. So you always have to add something on the end. Let's get down to pointers. Does everyone have pointers down, Pat?
No.
Well, there's
okay. I got a question on this.
Yeah, what's up?
I am so freaking confused. All right, I get what it's just. Okay, he initializes it as a pointer given the asterisks, and then
But-
when he
Nah, he just says pointer. I mean, yeah, when you make okay, you meant the volatile unsigned int initially.
yeah.
That's how you define the pointer, when making it in the first place.
Yeah. So, okay. And then when it's with an asterisk, it's pointing to a specific value. So when he adds 4, it adds 4 directly. But when he subtracts 2 as a pointer, it subtracts 4 instead. Why?
Ah, yes, the magic question. So
I hated this.
here's the
bothering me.
question. Here's the question. When you initialize the pointer, you're creating a pair of eyes, and that pair of eyes sees the entirety of the universe in one simple way. It's data type, and that's it. And it only sees one data type. Here we initialize the pointer as a volatile unsigned integer. If you remember, which you can still see it on the screen, an unsigned integer is 2 bytes. So what does that mean? It means whenever we do pointer arithmetic, which is math on the pointer without calling its value, also known as math on the addresses that the pointer is containing at the time, non-asterisks. So like line 9 is, basic pointer arithmetic. That's what that looks like. What we're actually doing is we're saying the address held at P, whatever that may be, which in this case he actually shows is F, 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 A, and then we say subtract 2. But in reality, whatever that scalar is, 2, 3, whatever it is, you multiply it by the size in bytes of the data type you initialize the pointer in. If this was initialized pointer in the form of a long integer, you'd be multiplying it by 4 as opposed to 2. And that's just because of a quirk of how the pointer works.
Yep.
And if you mess that up, you'll get everything wrong. So you need to remember that when you initialize a pointer, whatever its data type size is, whether it's a character, an integer, a long integer, a long integer, from then on out, the pointer will only see the world in that data type, and any scalar you give it for the purpose of pointer arithmetic will have to be scaled by the data type it sees the world in. Because think about it. If I say subtract 1 from the pointer be like 1 bit, 1 byte, 1 word. How far am I supposed to actually go? If you actually went 1 in the lowest sense, you'd move 1 bit over. That's useless. You get nothing from 1 bit, like my beautiful SRAM chip on my desk. It's useless, right? So the pointer needs a reference of how far it's moving whenever you give it. This is for our convenience. In reality, what you're actually doing here is giving it an amount of units to shift. And when you initialize the pointer, you tell it what its units are.
Okay,
An analogous system here is if you built a calculator to calculate how far away things are, and you have something that is a meter away, and your calculator's on centimeters, your scalar unit has to be multiplied by that. So if it spit out, if you said, yes, move me a meter, calculator, the calculator would have to do it 100 times because it's in centimeters.
Okay, and so since you initialized it as a
Unsigned integer,
and our memory is in bytes,
it doesn't really even care about, it doesn't even really matter on the memory side here. It matters on what data type you gave the pointer. So we gave it an unsigned integer, which is in 2 bytes. Remember, bytes are still technically an abstraction. It's actually really in bits.
So then it moves to FFF6.
because you gave it a scalar to shift the address by, and it needs to then multiply the scalar by its unit, which is 2 bytes. So you moved two unsigned integers. That's what you did. You moved 2 memory sizes of an unsigned integer down. Because the pointer, looking for unsigned integers, can only look for things that are as big as an unsigned integer. If you wanted the pointer, which is an unsigned integer pointer, to point to a long, it never would be able to do it, because it can only point to a half of the long at any given time, because it's initialized in how much it can look at a time. It's a pair of eyes with blinders on it, and those blinders vary in size based on the unit you give it.
So are you saying that because of our architecture that the only sizes we could address are a byte and a word?
Nah, it's in this case, it's the data type of your variable. So this is an unsigned int. On this table I have written down right here, this is not an exhaustive table, but this is most likely as many as we'd see on the exam. I doubt he'd go farther than this. A character is 1 byte, an integer is 2 bytes, an unsigned integer is still 2 bytes. We missed signed integer, but
I mean, we
that's-
couldn't actually have a pointer larger than a word, could we? That's not really possible with our architecture, is it?
you can actually.
Yeah, you can
When
do a double long.
ends,
You can do it with a double long, yeah, and it's pretty dumb. Wait, no, you can do it with a long.
It wouldn't be
or a
pretty dumb
double
if
long,
you were
both of
trying to
them.
find,
Well,
you're
it'll
trying to
just be a
move through
little
double
weird.
long numbers.
It'll just be a
So-
little weird. But the thing is, the glory of the pointer and why, when you think about it, you think, how is this useful? How is a pointer useful? Well, it's actually useful because of that exact case. When we're trying to look for stuff, if we wanted to look at a double long, we'd have to do a couple operations to pull each word out, because that's what we're addressable to. But the pointer looks for it all for us, which is hot. It's great.
And it can jump between.
And it allows you to
Multiple of
easily
them.
shift. So it's a way to keep your units straight, because it gives
Okay.
you get to operate in scalar. I say 1, 2, 3, 4, and that's unitless. That's just a number. And then the pointer takes the scalar and multiplies it by its unit, whether it be an integer, character, a long, and then it does its thing. So in this case, since it's an unsigned integer who wields the size of 2 bytes, you get to do 2 times 2 is 4. Thereby, you go 4 address or 4 slots down to get your answer, FFF6. Now, once you know that little bit, everything else kind of becomes relatively simple. You just need to know a couple little things. One, if you assign a pointer a value, if you do p equals a, what actually happens? When you do p equals a was, this.
Tells you to point to A.
A is a, what is this called? An array of numbers, of integers, of unsigned integers. But the thing is, you put the pointer is equal to A, so it's pointing to A, which is going to now hold the address of A, which I think it says in the question where A begins. Yeah, right here. FFFA, which is what we've been doing all this math on, is the base address. Now, this is volatile is this. Yeah, volatile is on the stack, right? When you initialize with volatile.
I don't know, but he always specifies it. They just all
Volatile.
assume all variables are allocated on the stack.
Yeah.
Oh, well, okay, yeah, okay. Then I don't care about
Volatile is just like you exit, it disappears.
Yeah, okay, gotcha. But even so, I was just making sure because the addresses were descending, so it had to be on the stack in that case. But yeah, when you say pointer without an asterisk is equal to something, it's going to be getting an address, because that's what that is. It will not pull values in that mode. You can only access values of pointers when you go into the asterisk mode. Now, here's the thing. When you go into asterisk mode, units no longer matter. We're working with values now, which means you're working with scalars. So this is not going to be 8. It is still 4. When you're in asterisk mode, it stays whatever the number is. You don't do any multiplication on your unit. You just get to stay as it is. And that's very easy. You can see, given this address, you just do this, done. Simple. And once you know those couple rules, how to assign an address to a pointer, how to do pointer arithmetic based on the unit you initialized it with, and how to access pointer values and do arithmetic on those values as you see fit. That's basically all you need to know in how to operate on pointers. Those 3 pieces of information are more than enough to get you through basically any pointer problem. Now, the good news is that these problems aren't actually that difficult, which is awesome because it's worth 20 points. That's a fifth of the grade on the final or on the midterm, and it's a pointer question. So if you really get your grind set in on the pointers, you'll be pretty good. And by the way, I mean, most people are probably going to stay home, but I was going to go to campus early because I'll be one of the people sitting in there like an idiot to take the test.
Same here.
But I was going to go to campus at like, I don't know, 11 tomorrow and just sit there in a room on the whiteboard and just do practice problems until it's time. If anyone else wants to show up, I'll say what room I'm in at the time.
Yeah, I got more reliable internet at home, so I'm taking it remote.
Easy peasy. All right.
I hated the way he formatted A, because I know he was just going step by step what was occurring, but wouldn't A for 0FF0 just be question marks due to the fact that we don't know what it is at that point? Because this is before the statement at line 8. So it would be questionable as to what that pointer is referring to. Until
I
A gets
suppose,
drawn.
yeah.
I'm
Yeah, I
pretty
was
sure
just
he had it
confused.
empty until he
Yeah,
went
he
with
probably-
it.
and then he
he
changed
just
it. That's why
populated
he
it, yeah,
that's
Bailey's
why
right.
he has it highlighted that way. Okay. So,
Hopefully he won't ask that kind of question. It's like, hey, what's in it before it exists? And it's like nothing.
No, it is nothing. The answer is nothing
it
or
is nothing,
unknown.
yeah.
It's unknown. Since this is on the stack, it's actually going to be unknown. Since in SRAM, whenever you turn that thing on, it just populates itself with a bunch of pseudo random states.
if you recognize any other problems like that, he has stuff filled in with question marks, which means we don't know what's in it. So that's why
Yeah,
it's that way.
he had that whenever he had a .c string with like an uneven amount of values, because half of it was filled with zeros for the null character at the end, and the other two were question marks because it just was unknown.
That was because we aligned it too, I believe, right?
Everything's word aligned here.
Yeah, I meant
Wait.
like on the homework. We had to align it, and there was those 2 question marks before.
Oh yeah,
Yeah.
stuff like that.
Ethan, what about line 11?
Oh, that's so line 11 is that's the syntax in C for incrementing something on its own, as opposed that's equivalent to writing P is equal to P plus 1. Now you see the phrase, so you see how we do P is equal to P minus 2 up there, and that's us explicitly saying we want to move down 2 units. So incrementing the pointer is, as I just said, P is equal to P plus 1. So what does that mean? You're actually doing functionally the address that's currently in P is equal to the address plus 2, because 1 is a scalar in this moment. There's no asterisks.
Okay.
So then it's going to be whatever that, let's just say the address is FFFA, even though it's not by that point. This would then be FFFA plus 2, not 1 plus 2. No asterisks in play means we're operating in the address mode. So you have to multiply the scalar number, being 1 in this auto increment version, by the unit, which is an unsigned integer, which is 2. So that's all that is. So that's the C. I never do that, except I do now, but oh well. I don't write, actually, no, I keep saying stuff, but I'm wrong. I write C almost daily now, which is such an unfortunate outcome. All right, so that is, really, it's no more work he did on this midterm specifically. So I have a bunch of his old midterms, and by a bunch, I mean the 2 he gave us. So let's see. Oh, that writing just stays there?
Yeah, because it's on your screen.
Yeah, I'm gonna get rid of that. There we go.
Just make it a permanent part of the background.
There we go. So this is one of his old midterms, and this is the unpopulated one. I also am in possession of his also uploaded answer sheets, but I'm keeping them on the back on a different file to give you guys the benefit of a chance to answer. All right, so first question is this assembly directive, which, as mentioned, what did we say about this thing? DS32 is probably allocating 32 bits, whatever that may be. 32 bits is going to be 4 bytes. 4 bytes. 4 bytes is 2 words, right? Yes.
Yeah.
And then guess what? Then there's a number 3 after it, which leads me to believe that this is probably true. 3 times 2 probably is 6. We don't need to know that, but I can tell you the answer is true. So never forsake logic. Next one, register R0 serves as the program counter. Yeah, true or
it's
false?
the status
True-
register.
True or
you know
false?
that.
True or false? If anyone says false, I'm putting them in front of Kim Jong Un or something. I don't know. I feel like I heard
Not
that somewhere
applicable.
before. Even so, C, we have yes. It is. Then the answer for B there is yes. The first register is program counter. Since if you think about it, the most important thing a computer can do is know where it's doing or know where it is and what it's supposed to do next. Otherwise, it'll just sit there like a Pringles can. All right.
Of all the things you could make it
Don't
similar
question.
to.
Don't question what I'd say. All right. Next one is C. True or false? The stack pointer R1 always points to the first free location at the top of the stack. No,
False.
No.
it's the last full location. Whenever
Yes.
you push something, that stack pointer is going to point to whatever you just sent onto that stack. Otherwise, the pop would make no sense. The pop, which is a simulated instruction from what I remember, or an emulated instruction, is, it pulls something off and then increments the stack. Since it doesn't make any modifications to the stack pointer, having the stack pointer pointing to a free location would make no sense and pop would never work. So it has to be pointing to a value after a push. Even so. 1D, the address range of a 1 kilobyte block of data placed in memory at the address 0x0200 is this. All right, what can you tell me about that 0? I said one thing earlier, but there's another thing that can't happen. In a word addressable system, which he doesn't specify this here,
Yeah.
I can tell you the answer is false. So he probably meant word addressable. Or I should
No,
say
it's definitely false because if you add 1024 plus 200 in hex, it's 600 in hex, not 800.
Oh, well, then it's really bad.
Yeah, it's really wrong.
Okay, never mind. I was thinking that this
That's
is going to be.
completely independent
I was
of whether
thinking.
it's
I was
word
thinking he was going to be.
addressable or
I
byte
think it's going to
addressable.
juke us. Yeah. Okay. Never
Now,
mind.
if he
Then that's
said,
really wrong.
if the address range of a 1 kilobyte block of data placed at word aligned addresses in memory that start at 200, it would be to what, 7FE? Or sorry, 5FE.
Yeah, because you just
You
said
added that,
600.
yeah.
Be 5FE. Yeah. There you go.
So you have to pay attention to the language.
Yeah, you won't see even it. This is a wrong range. It actually goes up to, as Sydney mentioned, 600. But then you have to consider the fact that in this case it's just wrong, so you don't need to think harder. But just because we know we're going to get these memory range problems, there's two possible things to look for. Most likely going to be word. It's going to be word aligned, which in that case, your last value cannot be two different values. It won't be an F and it won't be a 0. It can't be either of those things. It's most likely just going to be an E.
Yep.
Very, very likely. All right, back up.
For word or byte?
Word. Word specifically. Byte can, in fact, be that.
All
right. Yeah.
So always if you end up with like a 0 or F or E,
double
just
check
make
your
sure,
unit.
Yeah, double check what you're looking for, what the question asks.
And then E here, true or false. Instruction add R7, R8 requires 1 16-bit word to be encoded. Well, let's think about this. That just means this is basically saying, does this instruction require something to be in at least one of these registers?
Assuming it's MSP 430, yes.
Yes, because isn't it just add register to register
and then store into
operations
a
are just
register
one word?
direct, so you don't have to store another piece of data.
But here's the thing, though. Here's what this is actually kind of saying. It requires 1 16-bit word to be encoded. Now, this is somewhat of an ambiguous question because you could read it two ways, but I think we all read it the way that I think he intended. But you could also say that this question's asking that after you execute this program, will a word be encoded? Or our perception of it, which is in order to execute this program, must there be values? The answer is yes, obviously. There has to be something.
Yep.
Even if one of the registers is empty, it doesn't care. It'll put something else. You could even add 0 and 0. 0 is a value. That's not actually true empty. So even so, either way you take it, a word's getting encoded.
Yep.
Even if these are empty, R8 will then be populated with the result of empty. But it's still a word has been encoded and created. When you see encoded, just think of something overwriting. If at any point, if it's asking, did something get encoded, and at any point during operation, something was overwritten or changed, then yes, something was in fact encoded. This is a bonus. So let's see. How many memory operations, this thing again, will be performed during the execution of the instruction add dot word absolute F0000 and absolute F0002. He mentioned that this wasn't actually a thing because what was it? That address went into flash memory and you can't write to flash memory because it's read only. What I'm mentioning is F002 is the beginning of the flash memory in the MSP, which is a big no-no. You can't write to flash. That's it.
Oh no, those are labels.
Are they labels here?
They're labels. If it's absolute, they have to be labels.
Oh, okay.
Yeah, and what will happen is you'll have two words stored due to the absolute symbolism. The words that will be stored will be the absolute address of the memory location you want, instead of it being a offset from PC.
I just found something we're going to want to touch on, which is total execution time.
Yeah, that's another good thing to go over.
We'll do this real quick before we go back to those.
Yep.
So you didn't do this in class, obviously. Let me see if anything else. Oh, well. Execution time. So he's asking a question here. Says calculate the total execution time in seconds for the code sequence from above lines 0, 1 to 10. Check around. There's a jump. You got to consider jumps and such because what is it? Jumps take 2 clock cycles.
Yes.
He gives you the average.
Oh wait, yeah.
Pog. All right.
Yay.
All right. We know the following. The average CPI is 2 clocks per instruction. Assume the frequency of the clock is 1 times 10 to the 6th hertz.
Technical question. Even if you don't execute the jump, does it still take a clock cycle or no?
It
I
will.
believe
Yeah, it
does.
will.
Because it takes the clock cycle checking it.
It's got to
itself.
check it still.
Okay,
I think
so. No matter what, jumps
so-
always use how many clock cycles? per
Yeah,
instruction?
they always
If
use
someone,
the-
hey Ethan, you can check this on the homework.
what?
On the homework solutions, it'll be in there. There was a problem like this on the most recent homework.
Yeah, because I got the number of lines executed wrong. I had like 44, and it was supposed to be like 50 something. I think for the homework 33.
This is probably it. The solution.
Still waiting for my grade. It'd be nice.
You're waiting for 2, right? Not 3.
Just 2, yeah.
Yeah, I got mine back. All right, let's
What's
see.
the average right now?
Bad.
Not
All right,
good.
let's see.
Okay.
Where would you want me to go down?
Keep going. There.
Yeah, there. Yeah, see 51.
All right. You're given a CPI, which is your average clock cycles per instruction. You're given your clock frequency. That's the only information you're given. So then you have to calculate the MIPS rate for the code. So you got to calculate a couple values here. Wait, why did you calculate all this extra poo-poo?
Well, the top one's the number of instructions executed.
Yeah.
Okay, sure. All right. So let's go back to our this. No, it was this. There we go. So we have 10 instructions here. Let's quickly run through it in our heads how many times stuff happens. We do a sub, we do a move, we do a move, we do a bit set. Then we jump if not 0, or we jump if 0 to L skip. Now, are there any values anywhere? MyLaw is down. Okay, MYLW is down here. So this is what we have with that funky directive. So we do this. So we allocate for the stack pointer. We pushed it or moved it to the stack, and we incremented the stack, and or moved the second half of it up. Since I guess we can't move all of it at once, which makes sense because we have a lower word and upper word. And then we bit set. For some reason, we bit set the upper. I don't know. We bit set the lower here because of how
That's
the
a
stack.
bit test, isn't it?
Yeah, bit test.
Wouldn't it be the upper because you increment it, so it's on the upper one.
This is whack. So let's see.
The way I understand it is that the FFFA is on the lower.
It should be in the stack on the lower address, which should be the
Yeah,
most
and then
recent.
you increment it.
So yeah, we're operating on the lower. You're right.
No, we're operating on the upper
Well,
because you increment it with SP of 2 or 2 of SP.
oh yeah, yeah, Like indirect, or I should, what is
Yeah.
this, indexed? Poo indexed. So
Probably
yeah, we went
will
up.
need to draw out the stack.
I don't want to draw this die.
But also remember that my LW, that's not on the stack. That's in memory.
Yeah, that's over here, and it's putting addresses.
So
wait, no, it isn't putting addresses. It's actually straight up putting a word here and a word here because you allocated 2 words, and this is 2 words long. There's no immediate. You're actually putting the value in.
Yeah.
Ick. All right, let's go back to this because I don't want to calculate how many instructions. So here's what you need to do. Here's what needs to happen for a question like this. You need to, given a code block, know the amount of instructions that occur. Good luck. Then you need to
good luck getting that.
the ET here is the average, or the amount of instructions times the average times the total clock, which is a microsecond here. Because how many how many clock cycles happen in a given second for 1 megahertz? 1 million. Because what is the equation for frequency?
1 microsecond.
It's 1 over t is your period. So doing the math, you just do 1 over f to find your period, or also in this case, it'd be the period of a single clock cycle, which is going to be 1 over 10, or 10 to the 6th power. 1 times 10 to the 6th power is, as Sydney said, 1 times 10 to the negative 6 seconds, also known as a single microsecond. So when you do that, you take the amount of instructions times the average clock cycles per instruction times the amount, or basically times the period of a single clock cycle, yields you the runtime.
Yep.
And then MIPS looks like, what do you get the 2.5 from here? 2.5 is just the CPI.
Yeah.
Okay. So I guess he just does 1 divided by the CPI for MIPS. What was the point of everything else?
I don't know.
We're doing the total execution time. I don't know. It says there's only like 1 question here, but the first part makes it look like there's 2 parts to this question.
Yeah, he said calculate the total execution time, which is what we did here. Oh, he did ask 2 questions. Okay, those were, so this is if you're asked execution time, you do this process, these 2 lines. And then if you're asked for MIPS, it seems like it's just 1 divided by the average clock cycles per instruction.
Okay, I gotta write that down.
Millions of instructions per second. Well, I guess if it's in megahertz, yeah, that is the case.
Yeah.
Problem is if you're operating at different
frequencies. I guess here's probably what that is then. If it's average clock cycles per second, I guess, do you think the 1 is the leading on the megahertz? So if it was 2, it'd be 2 divided by 2.5.
Let's see.
I mean, let's see. What is there to prove? I don't know. That's me. That's conjecture.
Yeah, I mean, that's 0.8 MIPS if you have 1 megahertz. Yeah, this is why he said, like, yeah, this is a stupid way to like tell whether a processor's decent or not, because you just boost the frequency and boom, you win. You're Intel.
Winning. That's how it's done. I'm Intel. Let's go back to this.
Turbo boost time.
This thing. Back to the normal one since we just touched over that. So we did this, the encoded one. The bonus one was how many read write things, but I don't want to do bonuses. Bonuses are for losers. Let's go.
Well, we know that. Well, that one's pretty easy. Let's go through it.
Oh, fine. All right.
Thank you, Ethan.
What, to zoom in?
No, just going through it.
Oh, fine. No problem. All right. How many memory operations, read and write, will be performed in execution of this instruction? So we have a couple things. First things first, we called an instruction. What do you do if you use an instruction in this machine? Well, it says memory operations, which is read and write. So you have to fetch the instruction, which is a read.
Mm-hmm.
Then you have to decode the instruction, which is another thing. So that's instruction calls on their own are primarily just 2 operations in memory. Then, as Sydney just said, fetch operands. We have 2. That's another 2 things. Fetch operands.
It should only be 3 things. So you read in the word from
memory. Isn't it read operand, reads, or read instruction, read operand, read destination?
Yep. And then do your calculation.
And then write. So 4.
Write back in.
Write is the last one. So we have a fetch and decode on the add. We have
Oh,
a
that's
fetch.
weird.
We have a fetch and a fetch on the F000 and the F002, and then we have a right result. Now, here's the thing: the answer is 6 as opposed to our 5, and where we difference here is that he says it's 3 to fetch the instruction. So I don't understand that one there. It should be instruction fetch and instruction decode.
3 to fetch the instruction.
I don't know why it says 3.
Oh, because to do your operation, since you're
It's
using
3
absolute
words.
addressing mode, well, it's 3 words. So you pull in the 3 for the entire instruction and operands and all that. But then when you do your 2 operations, or
Yeah,
like you
so-
add the 2 together, you're still having to go to memory to find those exact values. Because when you pull in that,
Well, we're missing. We're
words.
missing just one thing.
No, it's
Oh.
3 to fetch the whole instruction, 2 to fetch what's in the F000 and
Yeah,
what
they're
F002,
pointing
and then
to.
1 to write to the final address,
Yeah,
whatever.
so
So then that's
6.
6. There you
6.
go.
All right.
Yeah.
Well, quick and dirty. Why not?
I had to think about that one for a sec.
So this is the funny hex, the wacky. These are not good midterms to give us for practice. Because I got
This is
the
intention all along. It's
no. I don't
It's
actually have a problem with it.
conspiracy.
We've decoded what these mean already. Even so, show word-wide hexadecimal content of memory corresponding to the follow sequence of assembly directives given the ASCII character for 2 different things: numbers and letters, or capital letters. So org, I guess that's a thing. Yeah, I have no idea how to decode what's happening here.
Yeah, that's our
org. Ours is not going to be
Is
like
this-
this.
what even is this again? Oh, assembly directives. Our directives look completely different.
I mean, yeah, that's why it's a
Because
little difficult.
even
to
is
compare.
dot even.
Okay, this next one.
PCA
This
is
next one's.
int.
This next one's good.
You
Yeah.
promise?
Stuff. This next one's good because it's got stuff like these. We know what these do. All right. What's the source addressing mode?
Absolute.
Yes. What's the destination addressing mode?
I'll let
Register.
someone else answer.
It's just a register. And then what is the source at? Oh, I'm gonna give you this part. What's the source address? That being absolute of Tony.
C004.
Yep. And there is no destination address because that John is a register. Registers don't have addresses. They're cooler than us. All right, let's see. Sub C, which is sub with carry, dot B. We have an ampersand and a register. What is that?
Indirect.
Indirect register.
Or
It is indirect, yes. But the thing is, another thing we're very accustomed to seeing is this with a plus after it.
Oh,
the
yeah,
auto
indirect.
Indirect
increment.
auto
No,
increment.
that's-
Yeah,
That's
okay.
different. That's
Oh, no, you're right, that
my
isn't.
point here is that's different. Register indirect is just the ampersand, but
Right.
we also are very commonly see another one that has, indirect part of it, but that would be ampersand, also known as auto increment. Ampersand with a plus after the register is going to do auto increment, and that's what that one. That's just a special case one. But yes, indirect is the correct answer here. And then the next one being 5 parentheses R5.
Is indexed.
Index.
Indeed. Indexed, our favorite method of traversing the stack like a bunch of wackos. Now we
Why
have
did
2
they-
things
why did
here
they even put indirect?
because they're chads.
Why?
Because they're chads. Don't
They're
question it.
testing us.
They're chads. Yeah, I mean, indirect's just gonna pull the memory. It's gonna pull the address as opposed to the memory of the
Same thing
register.
as saying 0 indexed. It's redundant.
Ick. Yeah, well, even so, source address here. Well, in this case, you have to know what's in R6. R6 contains this. So what, pray tell, is going to be in the source address? If given the information that R6 contains this, R6 being the source, ampersand R6 is the source.
821.
No, it's actually just that. It's just
Oh,
0xC008.
F014. No. No.
The
It's due to it
answer
being indirect.
the answer in
Register
the
indirect. It's pointing to a location in memory. That's your pointer.
yeah, the answer here in the what is it in the answer key says it's literally just what's held in the register.
What?
Yeah, no.
Hmm,
Yeah, because indirect, you're not getting the address of the register, you're getting the contents within that register.
Oh no, it asks for source address. I'm stupid. Yeah. Yeah.
Source is just that. Yeah, remember, there's no such thing as a register address. So if you're ever thinking, oh, what's the address of that register? You're not
Yeah.
having a
it's
good
not-
time.
It doesn't exist. Yeah.
Yeah, you're not having a good time. So on to the next thing, 5R5 being the destination address. I didn't ask for destination this time because, as I just mentioned, addresses don't exist for registers. They just are.
In a
So in this case,
Just jump
5R5,
on
given
a
the
bus.
information that R5 contains 0xC001, 5, that means you add 5 to this, John, yielding you, as Sydney mentioned, 0xC006. Now there's all this like wacky result stuff, but I'll leave that as a exercise to the listener.
no, not rotate right
Yes,
with Carrie.
yes.
Oh, boo!
All right.
Bye.
Now here, this is important. What's the source addressing mode of this instruction? What is it?
Why is it slipping my mind
That's,
now?
Symbolic.
Yeah.
that's all.
Wrong! There is no
Oh.
source address. There is
Oh, no,
only
it's
a destination.
What?
wait.
But
Yeah.
what?
Yes,
Wait.
there is only. This is a single operand instruction. So that,
there's only a
John, is
dest.
only a destination, because when you remember, the second operand in 2 operand instructions is the destination. If you take away the first, having just a source means nothing. You need to have a
Hmm.
destination, so you have to pick one or the other. Therefore, by definition and by requirement, single operand instructions must have only a destination.
Always
So-
check your cheat sheet as well, because it's also on there.
Yes,
I was
yes,
literally
it's just
staring
on
at
there,
it and
yeah.
still said there
It
was
is just on there.
source.
Which is a flex. So now, what is the destination operand addressing mode?
Symbolic.
Yes, it is symbolic. You got
Yes.
it right. You're just 1 box off now. As mentioned, what's the source address?
Nada.
Nothing.
Correct. And then the last thing is the destination address of Tony. So I'll bring it back up here.
Technically, isn't it using though the destination address as the source address because it's pulling the data from there? Did I just
It's-
confuse you all? I hope I did.
What's the destination address? What
It's
is
Tony? It's Tony.
it?
But the
I
source
mean,
is also Tony.
it is
Isn't it
so
C004?
it is
Isn't it?
C004. So the address is wherever Tony was, which, as mentioned here, since the address of Tony is this, then yes, that's its address. This is different. When like, that's why in this, since we're not doing this part, it's a little thing, but if we were to perform rotate right with Carrie, we would have to perform it on the content of Tony. Or as our God and Savior Monclick would say, the content of Tony. So that's 0xA821. So rotate right here is you just shift everything over. So best thing to do, in my opinion, for this is just write it out in binary and just shift the John over and then set your carry flag.
Chances RRC is a function on my calculator.
Well, it's
What-
also
what-
it's also on the
No.
so here, let's do this one. Let's do RRC here because it's a little bit of a tricky
How
one.
would you get the carry in that?
So here, let's see. So starting with 0x821 is what we have because that's what's actually stored at Tony. Now this result will, as mentioned, go into Tony once more, but for now we'll just do it this way. So let's write out that hexadecimal as binary. A is 1100, 8 is 0100, 2 is 0010, and 1 is 0001. So we have 16 binary digits. Now rotate right with carry. Is this the one that takes the carry off the end and brings it? Do we lose data here or do we preserve it? I think we lose data here.
Yep, it brings carryover.
Oh, never mind. So okay, perfect. In that case, we got to do some math. So this is doing it once. So we shift everything over 1 and then slap a carry on the end. So
This is assumed word, so the entire word, yeah.
yeah, so we're just
I
doing the whole
assume,
thing.
looking at the cheat sheet, the carry is
And now, yeah, it will.
Yeah, because
I can see
RRA
the
is,
result, so I
it's
see
got
what's
something
happening.
shifted in, so.
Now, if you just had RRA, which is rotate right arithmetic, you lose data. There is no carry being tagged on the left-hand side. But in this case, the LSB is, since we perform this operation once, everything is shifted over one digit. So the LSB, which since our hex number is 1, the LSB also happens to be binary 1, is popped off the end, stored into our carry. So the carry flag is 1 now. And then we shift everything over. And then we pop the carry on the end. So if we shift everything over, we will now have on the end, starting from the far or MSB, 1, 1, 1, 0. Then we have 0, 0, 1, 0. Then we have 0, 0, 0, 1. Then we have 0, 0, 0, 0, everything. And now the results of this operation should be D2, 1, 0. And the results in that, wait, no. Should be 4, not 2. What happened there?
I'm doing this in my head, so.
Well, I got.
We can't
A
see whatever
definitely
you're
goes to
writing.
D. 8 goes to 6.
No,
Wait,
eight, when you shift 8 over 1 bit, if you have 0, 1, 0, 0, and you move the
No,
single
4.
bit, no, it goes down 1 to 4 requires multiple bits. There's only a single bit, so it's got to be 2. So I think
Yeah, it's 2.
I think he has an error in this sheet here. It should be, because everything else is right. D4, 1, 0. So the middle one should actually be 2.
Yeah, I'd have to write that out.
Even so, the answer is D2, 1, 0, and it's because you pull the carry off the end, tack it on the other side, and then shift everything back down to fill the spot you vacated via the carry.
Wait, you're saying
The carry from the end doesn't actually go into the most significant bit, though, does it?
It does here. It does here. In arithmetic, you lose data. In carry, you save data, or at least that's what I'm looking at here.
I guess what I'm saying is the bit that you're shifting out is not the carry that's going into the most significant. It's only the carry that was already set, right?
yeah.
Okay.
So
Yeah, it
that's-
should be.
see.
Yeah, because in this instance, he tells you the carry was already 1 in the
Wait,
instruction.
so why isn't it D410?
All right, so I'll do this short part with the marker because it's only like a couple digits. So we started with the digit 8 in the 3rd hex slot. 8 in hex is equivalent to 0, 1, 0, 0.
In what world? What?
Bro,
What?
It's 8.
The 1, 0,
binary.
0, 0.
8 is 1000.
that's 4.
Ah, oof.
Yeah,
There it is.
yeah.
Woo, magic. There
We all
it is.
trusted Ethan so much.
Brain
Damn it,
fart.
Ethan.
Man,
Brain
I'm
fart.
depending on you.
It's
I'm depending
4.
on you for my grade.
It's 4. It's 4.
It's all lies.
It's lies. The cake is lies. Yeah, let's fix that. It is 8 is equal to 1, 0, 0, 0. Therefore, when you shift it, it becomes 0, 1, 0, 0,
So it
which
becomes
is
4.
4. So it's correct.
A gets shifted.
When you
turns
shift A is a special case because the carry is preset to 1, so you
shifted
bring
is
it in.
1.
So A, which is 1, 1, 0, 0, because that's 10, will yield, when shifted, you pull the carry onto the end. Carry was set 1 previously, so you pull a 1 in, then move 1s over, and you still have a 0. So this is D.
Wait, I thought A was 10.
A is 10. 8.
That's not 10.
Isn't that 12?
8. That's 12.
Ah, it's 10.
Ethan!
You have to draw out your
Bro,
hex
the midterm
tables
is
like I
tomorrow.
did.
Ick. It should look like this.
Beautiful.
This. With the
Yes, we
zeros
can,
and the,
What?
we can tell
What
what's
that-
going on there.
Yeah.
Yeah, we can read that.
it's this.
Okay.
This is A. This is, or yeah, this is A. And then when you change it, it becomes this, which is D.
Hmm. Isn't that 9?
No.
Isn't like A 1, 0, 1, 0?
This, yes, that.
Okay.
That.
Yeah, and then you
I've
then
been
add the
drained.
carry bit, which should be B, right?
Yeah, it should be D down here, and you shift everything over.
You will probably want to write out your hex table
1 0
tomorrow.
1 0, but then you add the carry bit. Does that not?
Yeah, the carry was a
1101.
You don't add it as an addition. You just push it.
It's 1101 then.
Yeah, I got you. Okay, that makes sense.
Oh, okay. There we go.
Now, since we're doing
So
this
let's
kind of stuff,
let's remember. Let's do this explicitly without the scribbles. A is equal to 1 0 1 0 for 10. When you shift it,
With the carry.
1 0 1, and that is D.
Yeah.
Also,
You
it also
shift it,
can
then
be
you
a
add the
NAND
bit.
gate. This is the shift in the
Wait,
this
okay.
bit is what came in.
So you just
That
tack
makes
on
sense.
a 1 on whatever emptied out.
You tack
carry?
on whatever the carry is currently onto the MSB.
It gets shifted to the most significant bit. Is
Oh,
the,
okay.
the
All right,
carry
all right.
because it's rotate.
All right.
Yeah.
Now, why wouldn't you? You're doing this individually by letter. Couldn't you just do this for?
I did the whole thing like on my paper.
You could
with-
do like all 4 segments together and then shift the entire thing,
That's
right?
the
Yeah,
best
that's what
bet,
I did on
yes.
page. Just shift everything and then reconvert. Do it in binary. It's
Okay.
best. But yeah, it's just how
All
it
right.
is. But technically, rotate arithmetic is just dividing by 2, so it should decrease. But this isn't rotate arithmetic. This is rotate carry. Everyone like my NAND gate.
Does rotate right arithmetically is where you keep the most significant bit and copy it, right?
Yeah, because you lose data. You're not resetting the carry or anything. You just keep whatever the MSB was, keep tacking it on.
Well, it's the sign bit that stays.
Yeah,
correct?
which is the MSB.
Yeah.
All right, let's bonk. And my favorite logical operation. Well,
Oh, it's in hex.
what is this? What does this mean?
That means an immediate,
It's
which
the
is probably
craft.
not a constant.
What does this mean?
That means
Index.
Indexed. Yeah.
Correct.
totally knew that off
Indexed.
the
It
head.
is indexed. We have immediate and an index. Now, tell me, what is the source address?
none.
Correct. There is no source address in immediate. You're just giving it something. And then
Destination address.
what is the destination address of R6?
Whatever.
It's R whatever, it's whatever
Yeah.
shifted. So let's go see what was in R6.
C0. So C006.
Correct. We shifted it down by 2. So we subtract 2 from whatever was contained, or what I should say, whatever was inside R6, subtract 2 with this. And now you have this.
Oh,
Or
And that's the
Marculi.
address it uses,
and
right?
then you,
Because R6 is holding an address right now. This one. So
Uh-huh.
when you do R6, which technically is just, this could also very easily just be like a variable or something holding an address, whatever you want, but we use registers. Register holding an address, because this is an address right here. We want to go 2 less than it, which a 2 is just a shift of 1 unit address wise, but yeah, it just goes to C006.
So the thing that we're actually anding is 33F4, is that right?
We would, be anding, the value here, I believe.
you'd
and
have to do
this.
that bitwise, which would be a pain. in the-
Correct.
Unless he told you to do it dot byte, which would have been nice, but
Well, he didn't. He said bitwise, so
Yeah.
get wrecked.
no. If he had just told you to do it with respect to a byte, so
Yeah.
you didn't have to do all 16 bits.
Oh well. I mean, the good news is like that erases a whole thing right there. That's 0. So you can already cut out 4 of them. Quick
Apparently, I have
note.
an and function on my calculator. Let's see what this is.
I would assume it's an and function, but the thing is, quick note for and, the controlling value for and is just 0. If you see a 0, you can immediately stop thinking because it's just going to spit out zeros.
Mhm.
Uh,
What is the value that we're anding here? Go back up.
That would be 33FF, or no, 33F4. 0x33F4 is what's contained at that location.
And how do we
Syntax
know that
wrong.
again?
All right. R6 contains this address, C008. This
Okay.
instruction, says, I want you to go -2 units up from this. Well, this is just address math. So you do subtract 2 from the address. Boom, gives you
Oh.
006.
That makes things easy.
That's what's contained at 006.
Okay, sorry.
Bitwise logical AND of this with this. So the first thing you know is the results, the M, like the most significant hex digit immediately drops to zeros. Why? Because the controlling value of AND is 0 and this is all zeros. That deletes. And then you just
So
do
it goes
bitwise
2C0?
comparison 1 to 1 to 1. So the result is 0x0AC AC2. So let's go look at this.
2C0 is what I get.
2C0.
Mhm.
This guy's result is 0x0AC2.
2 ANDed with 4 is going to be 0.
Allow me to
C with 3 is
do
going to be
this
just C.
bitwise. 1 1 1 1 1 1 and 0 1 0 0. And then we come down here for this, and I do 0 0 0 0 1 0 1 0. C is 12, so 1 1 0 0, and then we have finally 0 0 1 0. This yields 0. Now you'll get there might be something tricky
I got him.
here.
I got him. I got gold bag.
What? He's got a thing. So this is interesting.
What is A?
I mean,
Oh, I
Can't we
think
just-
I think there's a quirk here. So his result is no, you're right. His result is in fact 0x0 2C0. So yeah, no, there's no quirk. It's just and. I was reading the wrong
it's just
line there.
bitwise
We're
and.
good. Yeah. So this is just everyone knows how to do and. If you see a 0, it's a 0. If you see 2 1s, it's a 1. So you just compare bit to bit of this hexadecimal string to this hexadecimal
Or
string.
if you have a calculator that can do it for you, use that.
Yeah, you and your calculator. This is
Imagine
Pog
being
Loot.
that fancy.
Look at this. Analyze assembly program.
Oh,
I want to hurl.
no.
Woo!
God.
This is what we're talking about. All right. Let's get some stuff out of the way first. How confident is everyone in their ability to run programs in their head?
Not.
Okay.
Yeah, no.
Are there
Especially
any
when it comes to looping?
Are there any particular pain points?
Conditional jumps?
Really? Okay.
Yeah.
All right. Conditional jumps. They care about flags.
Mhm.
So here's something you need to keep in mind when analyzing code and when writing it yourself. Sometimes we like to just do compare statements and then jumps, and that's fine because whatever you compared will set the flags in a way that I hope you meant. But sometimes people get a little, a little brain fog, and they'll do their compare statement, and then they'll do something like a sub or an add to do something unrelated, and then they'll do a jump. Don't do that. You need, when you set flags for a test condition, you better have that jump immediately after it. If that jump is anywhere else, you've created unpredictable program flow because you can't predict what the flag states will be at any given time. And then just in case, you also don't want to get into infinite loops. So you need to make sure that your flags are being updated loop after loop and they don't just hold. So you need to also make sure that some other instruction is either clearing your flags if you need to, or you do another compare before you reach the next jump. Otherwise, your flags won't change and the next jump will be pointless. But in general, the jumps I use most often are jump if less than, jump if equal to, and jump if not 0, and jump if 0. Those are the ones I use. Yes, there's jump if greater than or equal to, I think, which is JGE.
Mhm.
But I don't think that's actually all that useful. And you can basically, with regards to greater than or equal to or less than, you never need to use greater than or equal to if you don't want to. You can just, finagle your compare statements and the order of your values to do less thans instead. Another good thing that Gady taught us is sometimes instead of testing for the condition you're looking for, you can test for the opposite of it. test for its inverse. And in doing that, when the inverse doesn't happen, you know that, hey, my condition happened. So testing for the inverse most of the time in programming allows you to speed up program execution. Don't ask me why, it just happens. It's just a thing.
Well, if you look, you're looking for most
You're looking
of the time here, you're looking for, if you're wanting to jump past something, you're looking for the inverse condition anyways.
Yeah, which is good.
Since we don't have conditional instructions like we did in ARM.
Yeah, all my homies love the if statement, but we don't get that over here. So another good thing to note, unconditional jumps, they're awesome, but they're also dangerous. If you put that in the wrong spot, you lose. So you have to make very sure that that unconditional jump, in my opinion, unconditional jumps only should exist for two reasons. A forced loop that if there were some error that something didn't catch, your program wasn't built to catch certain data, it will still set you back. Like let's say you're incrementing over an array of integers and doing integer tests, and some numbskull put a character in your array. So it misses all the tests. And most people have that end statement at the end of their programs. Your program ends early and you have no clue why. And it's because someone put a character in your integer array. But if you have an unconditional jump protecting you from that, instead of getting a program that stopped prematurely, you get a program that has the wrong value for one test, but then keeps going, because I assume if you're going over, an array, your jump conditions increment to the next value. So you can skip over error values as opposed to just ending the program. But that's up to you.
Pretty much the absolute jump should just be at the end of loops.
Yeah. So he has
You've
a
got
couple
for
ways
loop
here. So you
going
have
or
an
while
end,
loop.
you have an end here, and you have this. So you have a jump to this, which is a jump to itself.
That's just so the
Which is
program
which just
doesn't.
finishes itself.
Yeah.
And then you also have end. So it can reach two ways. You can have a jump to this label and it'll reach this. Jump to itself.
Go
It also
into an
knows to
infinite
end.
loop.
Yeah, there's a lot of different ways to tell it to end, in my opinion. Just tell it to. Okay, there's a quick other important note of things we're going to want to know for program stuff. So in the line of program, there's really not much I can do to make you a programming god in the next 8 hours or so. Unfortunate, but really, reading code, we have the ISA, so we know what the instructions do. Sometimes, it's just about trying to figure out why it's done the way it's done. And that's just, it comes with experience, unfortunately. So if you haven't been sinking a lot of time into practicing stuff like that, it's just how it is. Probably do better on the final if you sink more time into it. But it'd be like that sometimes. But important notes here. This is a normal program. Nothing special, nothing too special here. This is just a thing. There's no functions. This exam does not have ISRs, correct?
No, it does not.
Good. But we do have subroutines. Important, because guess what? We're going to get a question where he's going to give us like 6 lines of stuff pushed onto the stack. And then he's going to say, write a subroutine to do this with these values and then return it this to me. So you need to know how to write a subroutine. So we've seen subroutine stuff over here a little bit. So I want to get up here to note some stuff. So subroutine. Important quick thing to note here. How many words were pushed onto the stack?
Two,
How many words were pushed onto the
Oh,
stack
wait.
with these 5 lines?
5.
3.
5.
5 lines. 5 words, I mean, yes, 5 words. So here's
Yeah.
why. You push the address of your thing. Then you push the upper 16 bits. So you pushed a word of the scalar, upper word of the scalar, lower word of the scalar. Then you push the size. So that would lead some people to believe that it's 4. And a lot of people would say 4, but then we called it. And the only way we're getting back out of the subroutine is if we store the program counter when we call. And that's what we do. We put the current, we put the next, we put the next instruction to be executed. Its address, its program counter value into the stack via call. And that's what that does. So that's just that, but that's just stuff to remember. And because this PC value is pushed via call, you need to be very careful about what you do when you're in your subroutine as to not overwrite or lose track of where that value is, because otherwise you ain't coming home. ET's not saving you, you're just stuck. And that's unfortunate. So we came here. Now, what did he do here? Why did he do this? Because he chose to use his registers. Will he take off points if you don't save the context? Who knows? Really not that hard to do it. Just do it. if you use registers. Now, if you wanted to be a crazy person who did everything in like stack arithmetic and did no math on the registers, that's up to you. I wouldn't do that. But even so, important parts of a subroutine. You need to put this line in because that is where it enters the subroutine. If this label isn't here, this code means nothing. For all he knows, this could just be, you know, sitting somewhere in the ether. This ain't getting there. If you call this and this label isn't there, he's gonna take some points off because you didn't write a subroutine, you just wrote some code. Even so, I don't know if he'll take points off, but just do it, saving the context. And then I don't know, did he restore yes, he then restored
He
the
restores
context.
context, which is very important because if you want to use the return statement, it's just going to look where the stack pointer is.
Yeah, you're gonna have a bad time if you don't do that. So that's the thing.
So if
need
you
to
like
keep track.
return, it'll try and pull, you know, say R12 or
Yeah, so
R13.
we'll go over this real quick. So we
It'll,
just
like,
see
return to whatever
we
R13 is.
did 4 pushes and then a call. So the 5th item we just sent onto the stack is the PC, and we need to keep knowing where that is. We've entered the subroutine. We then pushed 2 more things. We performed 2 more operations that added 2 more words to the stack and decremented the stack pointer by 4. Okay, cool. We do our operations, we do our math, no problems there. But that's the thing. You need to keep track of how many stack pushes you perform within the subroutine. Doesn't matter what you do outside of it. Because once you've entered the subroutine, that's your starting point. That's the address you need to return to. So you need to make sure that your stack pointer is pointing here by the time you've finished. So you keep track of the amount of pushes you perform within a subroutine, and then you must perform the same amount of pops. Otherwise, that return address is going to return to a value or something, and then you're going to be either at some random line in your code, or more likely, your code's going to error out because it's going to say, hey, bud, when I've compiled your stuff, the program counter only went up to this line. How did you get up to FFFFFFF? I don't know how that happened. And then you're not going anywhere. I did that. I had problems on one of my programs where I had to do some funky stack math in order to find my return value once.
It's
not
just
fun.
magically works.
Yeah.
Don't believe in it.
Yeah, don't make mistakes.
A big part of this is being able to draw out the stack.
Yeah, and then another big thing, if you don't have a return statement, ET ain't coming home either. So you better put your damn return
Yeah.
statement there. Otherwise, you
So
have a problem.
Whenever you build one of these, what I like to do is I like to build the outline of the program first. So like sub S, you know, your label, then your return, then you can start putting in context that you want to save. Then you can pop your context out. I work in a non-linear fashion on these, and that might help some people.
Yeah, and as Milenkovic
You might
stated,
get partial for it.
as Milenkovic stated, we are not programming experts by now because we are children compared to the embedded systems gods of the 80s.
Mm-hmm.
Because of that, do everything else before you look at the programs. I mean, you could take a peek and start working them in the background while you're doing other stuff, but get every other thing written out first before you start looking at the programs. That goes for code analysis too. Do code analysis before you do code synthesis. Writing your own program will always be more complex, or at least depending on the question he gives us, just assume the programming will be more complex than figuring out what his programs do. Most people have more trouble in writing the program anyways. And also, another quick hint or another quick trick, since we're allowed to jump back and forth around the test, a good thing is that we're being given questions focused on code analysis. So he'll give us blocks of code that for all intents and purposes, as far as we're aware, work. Because of that, you can use code on the exam as an example or reference for when you're writing your own program. A lot of stuff in programming transfers program to program. So just as a general test taking tip, this worked in Gady's class as well. The exam has, you know, like 25% of the code you need to write is probably written on the page in the last analysis question. So being able to pull stuff out and use it is fine. Most of programming is taking someone else's library and using it for your own purposes. You know, it's just how
90% of the lab right now.
Exactly.
That's how
it operates. Yeah, that's what happens. That's just how it is. You know, programming, you can solve it a million different ways. It just so happens everyone solved it the exact same way, completely uniquely. Don't question it. That's just how it is, right? So that's that. Any questions on programming or any specific like pain points that you'd like to discuss further?
Just the necessary as long as you have the first label, the same amount of pushes and pops, and then the ret. That's all you need for
That's
the
the main,
basics.
yeah, that's the main composition of a subroutine. Everything else is just programming around it and just
Okay.
doing what he tells you to do. But if you want to call what you wrote a subroutine, you need the label he tells you. You need the pushes for saving the context. You need the same amount of pops as pushes to restore the context, and you need the return statement. But that is all. Everything else is up to your discretion because, you know, coding is unique. So do as you please. Hopefully do it correctly, but oh well. That's that. There's really not much more I can think of. Is there any other topic? I mean, we did like MIPS and stuff. We did clock calculations. We did pointers, and we really went in on pointers because that's all like 20 points for easy money. As Milenkovic
Just want to do a
stated.
code analysis. What was the last?
I
one we
really
were
don't want.
looking at?
The thing is, doing a code analysis
It
doesn't
wasn't
really
that
help
bad.
much. Ugh.
It just takes a lot of time,
Ugh.
though.
Ugh.
No, just like explain what it does. What was the last one we were looking at?
It's probably on.
May have been on the other page. There, yeah. So like he may have us describe something like this in words and what it does.
Here's the questions. How many bytes is used to store the string at label greet?
1,
Yep.
I guess.
Wait, no.
No, that's 8
No,
per character.
Okay,
Yeah.
this isn't
Per character plus null. Maybe. Is this C string or string?
It's none. This is assembly.
This is okay. We won't have the DC8 in our test, right?
It's pretty
We
sure
won't,
DCA just
no.
means word, but we won't. That's just because
That would be byte. So in our case, this code would be written as
It's 1,
greet
2, 3,
colon byte for some reason, which probably not. And then hello midterm.
15, 14, or 15, depending if you have a null character. That's how many bytes you'll have.
No null characters in assembly strings unless you explicitly place it.
Yeah. So if it's
Unless it's C string.
okay.
This
Yeah,
isn't C string. This is assembly.
I don't know. That's the thing. I don't know if you putting it in quotation marks makes it a C string in this old archaic language.
This is the same code. No, that's the thing. Okay, here's the thing. Assembly directives differ based on architecture. We're using the MSP, which is why ours are. Everything else is identical. So this is assembly program. C string does not exist in assembly.
Okay, fair enough. Fair
you,
enough.
Like build it. That's why when Milenkovic demonstrated this, he had like an extra thing.
Actually, no, that's a lie.
With single quotes and a 0.
Are you
I
sure
can,
about that?
I can pull
I'm
you
pretty
up
sure
my old
it's-
program.
Well, you
Yeah,
can
it's
use
dot
you
C
can-
string. You can do
Yeah,
that
it's
in.
literally dot
Dick.
C string, and the only difference is it puts the null
Ew.
character at the end.
Ew. I don't see a
Well,
dot C string
that's
here.
the thing. We can ask him if he does something vague like that, puts DC8. It's like,
Well, he's not gonna do that.
string, you know. If I'm just saying, if he does, that's not something to get hung up on.
Well, yeah, even so, but this is gonna be byte, and then I take it. This is
It's just how many
technically an array,
characters.
so it's yeah, you just count characters, including the space. No null string here because there's no C string anywhere, and there's no null character defined
Wait, so,
after.
okay, so including the space, it's what?
16, 15.
6,
But
12.
it's 14 plus the
I have
null.
14. So it's 14 bytes.
Should be if it says
It's
byte,
just
then
how
it's
many
allocating.
characters, yeah.
Yeah, it's
Okay.
allocating a byte per unit because this is technically an array of things.
Ooh, I'm
Array of
hearing
elements.
thunder outside. Yo.
Pog.
Yeah, it's thundering back.
Yeah,
So, so
also
what's the
just-
answer for that?
this would be
can't count.
15, I believe, or 14, however many in this instance, however many characters there are here.
7,
So that's
it's gonna
14 characters.
14, yeah.
Then we have 14 bytes because this is allocating a byte per member of this array. So
So if it's a word, it will just be multiplied by 2.
Pretty
yeah,
much, yeah.
or in this case, if it said how many words and you labeled it as follows, then you divide it by no.
But then you would divide-
it
I
by
mean,
2. Yeah, but it's
right?
it's a
Yeah.
whole other thing. Yeah, you divide it because you're working a smaller unit. Even so, what does the instruction at line 13 do?
What is 13? So it moves the base address of greet in R5.
Yep.
Correct. That's it. All right. What does the program do? All right. Good night.
Add code comments. Oh, there you go.
Yeah. So this is the stuff we have to do. You have to add code comments. You just say what each line does, and then when it says what the program does, that's not via the code comments. That is you write here. What is this
Yeah.
doing? Now, what is this doing?
Checking
Oh,
arrange
ew.
different letters. So
Yeah.
it's just like uppercase is gonna transform into lowercase.
Yeah, I think it's something like that because it's comparing the letter to R6 being what is currently holding. R5 gets the base address, then we auto increment along this
And then put in R6.
array
and then
and
check.
R6.
Yeah.
So R6 contains a single character at a given time. I don't know why it's doing the test bit stuff on its own. That's a whole other John. That's what the ISA is for.
Yeah, but the
It's
comparison.
testing
Yeah,
if it's
he's
0.
It's
Yeah,
So
he's
it's
comparing.
testing if it's null.
Yeah.
yeah. Oh, yeah. That's what that is.
Oh,
So
okay,
And
so you
that
can just
L.
quit.
Oh, what does the L exit do?
That's
it
just
ends
this
the
goes down
program.
here. It goes down here.
Why
It
would you?
finishes.
Oh
Because
yeah.
if it's
because
0,
it's
if
null.
it's 0, then
Yeah.
it's the end of the
Yeah.
string.
Yeah.
Yeah, so
and
it's
then-
it's literally just
Smart,
changing all
Sydney.
uppercase characters to lowercase.
Is that what it's doing?
Yeah, because he's adding
D
the
plus
+1.
So it's from A to Z. Check.
Yeah, so
it
that
from A
compares to
Z.
see if it's in the
Like
upper
uppercase.
range, and because the uppercase letters are lower on the ASCII table than the lowercase. Yeah, so it's literally what we did for our lab.
I don't think it's
Mhm.
updating the.
No, it's not. It's not. Okay,
Counting.
it's not changing the characters. It's
not?
I think it's
It's
counting.
counting-
It's counting letters. I think.
Yeah.
Oh, here, watch.
maybe.
Let's test. It's comparing A
Oh.
and R6. If it's less than A, it skips to L next and checks the next character.
So it doesn't
If-
increment
if-
R7.
So this,
which is a
if it's
counter.
anything that's not a letter, and then the next one, what's this doing? This isn't actually incrementing it. What it's doing is because he used jump greater
Oh.
than or equal to, which means
Oh, yeah,
Z
yeah.
plus 1 is an equal to condition, so that's satisfying everything, which also jumps to L
Including
next
Z.
and skips. If not, it increments R7, and then at the end, we're moving R7 to P1 out. Therefore, R7 is just counting the characters. This is a
Yeah.
character
Oh
counter.
no, it's counting the
The
uppercase
uppercase letters.
characters.
Uppercase characters.
Uppercase
Specifically.
character.
Letters,
It has to
yeah.
do,
Okay.
it has to do the +1 in order to include the Z character, because that was something that got me
Well,
on
in this
an
case,
assembly.
because it's jump greater than or equal to, it's including the character directly
Next to
following
Z,
Z,
which I believe
because of the equal to condition. It is
Mhm.
colon.
Yeah.
That's what that does.
So instead of specifying colon, he just said Z plus 1.
But he very well could have instead say compare colon and then have done jump greater than or equal to, and that would have been the same thing.
Yeah. It's because of the greater than or equal, he has to go to that upper.
But I think in this instance, that's how most people would have done it. But in this instance, he did it this way as to not confuse the students, because just the fact that you see an A and Z, you're immediately, led off to the fact that it's something about characters.
Yeah,
Or
it's
uppercase
something
characters
to
specifically.
do with that range. So it's either
Yeah.
counting outside or inside.
If he had given you the colon, he definitely would have told you what the colon's ASCII
Mhm.
table
Mhm.
value was. But that's like basically code decomposition analysis is just 100% running it in your head and solving the puzzle real fast.
Mhm.
Emphasis on not real fast.
Yeah.
Scroll
be like
down.
this,
Scroll down.
It's saying what's the
It
value,
went
so it's just the
out by
count.
the end of the program. So you have to.
Once you
Oh,
know,
now that you know what you're
1,
doing,
2, 3, 4, 5, 6,
so
and that's it.
6.
6,
That's
because
it, yeah.
lower cases don't count. That's it. Checkmate. Don't even need to run the program once you know what it does.
Yeah.
That's part.
Scroll down
Uh,
again. Just get through
Estimate the execution time. Woo!
No.
Now you have to count how many times it is.
I
Well, how
quit.
many times it loops? So the problem is, it's one of those. It's not just a solid. Like,
Yeah, it's because they're gonna have this, which doesn't
Oh my
actually happen.
gosh.
This condition's never satisfied based on the input array.
But it still counts as an execution, though.
Correct. We still have to burn some stuff.
What
But
do you
the
mean
thing
it's
is-
never counted? There's a space and there's an exclamation mark.
No, but this. That's
Oh,
what's-
Yeah, the
that's-
jump, even though if,
The jump
even if
less
you
than
don't
and greater
execute
than
the
will
jump,
catch
it still
those.
counts as an
This
instruction.
jumper 0
Yeah.
is testing for the null. That's what that's doing. Literally the null character. That's
It's
what
like
That'll
that's
take a
only go
counter.
once. Those
and
instructions
that will never be tagged here because there is no null.
Mhm.
Actually, there's not
I know, there
explicitly
won't be
one,
just
but it has to stop somewhere.
Okay, so I guess we do assume there's a null. at
I
the
guess we
tacked
have
on the
to,
end.
because otherwise this
Yeah.
doesn't stop. Actually, no. Wait. No, yeah, no,
it's
that is
infinity. There's no
no,
null.
no. That is there is an okay. So we have in this case we have to assume the null character is there because the only condition that gets us to L exit is that test condition
Mhm.
to give us the move to P out. So we don't get a result unless we get null.
Is there any jump to like end?
No.
Why is that included?
I think that's similar to how
That's
we.
that's what I mentioned. So you see how his this is his actual end condition because that's what's actually
Yeah.
going to be reached. But it's good practice that if by some miracle you somehow jump to greet, which won't happen, but why did he make it a label? Because of some weird directive rules, I guess. But if you somehow jump to greet, you just go to end.
Right.
If you don't have end, you're gonna have big. Also, by the way, you have to have end.
Yeah.
At least you have to have this. You don't necessarily need this label, but you need to have these in your programs. Otherwise, they get angry.
What? Just as you have to. Oh, that's actually he will count us off for the watchdog if we don't have the watchdog statement. Just as a reminder to people.
Lucky
Wait,
us, as I
really?
mentioned, don't need to memorize the watchdog statement because he gives it to us. But that's the thing. We won't be writing any code that will have us do that because I think we're exclusively writing subroutines where that will be handled for us.
Yep.
Which
Or
is
either
awesome.
he'll put the watchdog thing, because
Yeah,
that's sort
as
of a
part
hard
of
thing to
it.
remember first.
It is a trick, but that's my point earlier. Just copy it from somewhere else. It's gonna be there. I know it will be. So just take it from somewhere else. But yeah, that's that. Any other questions? It's running a little long, almost to 2 hours.
I think that's it for me.
Yeah.
Yeah. I'll
Oh,
probably
damn.
show up early too tomorrow. You said 11, Ethan?
Imagine. Yeah, I'll try my best.
Okay.
Would you be willing to Zoom that as well, or no?
Typically, we just do it.
Yeah, I won't be able to pull that one off.
Okay, all right. I just wanted to check
Because we're usually
No
taking
problem.
rooms adjacent to other rooms,
okay.
and then
Yeah,
we
we
never
just-
know if they're ever just going to get taken or not.
Yeah,
so-
we normally get shifted around a couple times because people just walk in and then they say, yeah, there's a class in like 5 minutes. I'm like, damn.
Yeah.
I'm taking it remote. I got a better internet here, and I don't trust school Wi-Fi.
Yeah, that's what I'm worried about.
I don't like
Actually-
taking it in my room.
The thing is, I trust school Wi-Fi more.
Yeah,
than
Sydney
Scottsboro.
lives in the fucking boondocks. I don't know where he.
Oh.
It's not even the Boondocks though.
I don't know what is the boondocks, as in it like terminology wise. What does it represent?
Not near
Is it
a
just
city
is it
park.
just rural? Stop the share.
Yeah, let's go to Google. Let's see